screen, doesn't it? So we were talking last time about first order differential equations, and in particular that they're separable and separated. They're separable if you can write them this way, which is to say separate the variables, and then if you integrate both sides you get a solution. An example is the logistic equation, which is interesting in its own right. If we integrate it, what we do is we set f equal y over capital Y, and then we can write it. We can rewrite the equation this way and integrate it, and then one can write it in this form as well. Quantum chromodynamics is a theory in which the coupling is strong where it's most interesting, namely at the sort of distances that presumably explain quark and gluon confinement, which I should say is really a mystery. One can replace space-time with a four-dimensional lattice and replace the gauge fields with group elements, and that's called the Wilson simplification of the Wilson ansatz. And you then get good evidence of that quantum chromodynamics. You can do the calculations on a computer, not numerically, non-perturbatively. You evaluate the path integrals, and that gives good evidence that quantum chromodynamics is the right theory of the strong interactions. But it's still true that there's no actual mental understanding of what's going on with quantum chromodynamics. All you know is when you hit carriage return, a few moments or days later you get an answer that's correct, but you don't know how the computer did what it did. Or, I mean, you know because you programmed it, but there's no real understanding. In any event, there's something called the beta function, which is minus the derivative of the coupling constant with respect to the lattice spacing. And in particular, if you use the first order approximation that beta is cubic and the coupling constant, this definition becomes this separable differential equation, which you can then integrate. And the amusing thing is that it integrates to be an exponential with an essential singularity of g equals 0. And that's quite interesting. I think I mentioned that to you people in class, either in the problem session or the real class, as an example of an essential singularity. You can invert this and you see how the coupling constant varies with the distance, with the lattice spacing, and small lattice spacing corresponds to high energy. That's the usual uncertainty relation. Distance times momentum is a constant. And so as the lattice spacing goes to 0, or equivalently the energy that you're studying goes to infinity, the coupling constant decreases logarithmically. And that means that at the Large Hadron Collider, one can use perturbation theory to compute cross-sections, strong interaction across sections, even though, whereas at lower energy, instead of, say, 10 TeV, you're down at 1 MeV, which is 6 orders of magnitude less in energy. You can't compute those things. Sometimes separability is hidden, and in that case, for example, you have an equation like this: P of x and y dx plus Q of x and y dy is equal to 0. Now, if P and Q are both factorizable, then you can, in fact, separate it. What you do is you divide the differential equation by R times V, and then you can find that it's separated and you can integrate. So an example of this is this particular differential equation. It starts out looking as though it's not, it certainly isn't separated. But P and Q are both factorizable. In fact, they're factored. And if you divide by this product of factors, you get, in other words, you divide by the y term that multiplies dx and by the x term multiplies dy. When you do that, you get this differential equation, which you can then integrate, because this and that are both logs, and numerators being derivatives of the denominators. Now, exactness is something that we can understand in a deeper way, rather than just realize that, rather than just looking at the equation, we can actually understand it to some extent. I can maybe use the blackboards to talk about this. And so what we have is we have P of x and y dx plus Q of x and y dy equals 0. So that's our differential equation. By the way, I'm very happy that the department has adopted the chalk I recommended. In fact, they made it obligatory in the new building. So if this is exact, if this is actually equal to the differential of some function of x and y, in other words, this is the x derivative of phi times dx plus the y derivative of phi dy. And so that's what exactness really means. And now we can understand it a little bit, because we can say here that P is phi sub x and Q is phi sub y. And then what you can realize is that P, the y derivative of P, is phi xy, which is the same thing as the yx derivative of phi, and that is the x derivative of q. So if this is exact, which is to say it's the differential of some function of x and y, then the P has to be the x derivative of that thing, or that function. Q has to be the y derivative, and as a result, the y derivative of this term has to be the x derivative of that term. And this is called the condition of integrability. Now, obviously, if a function is, if a differential equation is p of x dx plus q of y dy, in other words, it's already separated, then it satisfies the integrability condition because the y derivative of p is 0 and the x derivative of q is also 0. And so 0 is certainly equal to 0. And so the thing is exact. Maybe for these examples, I'll use the computer in order to go through them a little more rapidly. But these examples are, of course, physics examples, so there's physics in these examples, and that's why I chose them rather than just arbitrary functions of x and y. So Boyle's law is an example. At fixed temperature T, the changes in an ideal gas, the volume and pressure of an ideal gas varies this way, PdV plus PdP equals 0. That's exact because it's just the differential of the product, PV. And so PV is a constant, and the constant is something we call the temperature after we factor out the number of particles in Boltzmann's constant. A more accurate formula was proposed by van der Waals. In fact, I think he did this in his PhD thesis, which is fairly impressive. What he suggested was that we subtract from V something proportional to the number of particles, and that B prime then is like the volume of each molecule. And then we also add to P this term, and that term represents the mutual attraction of the molecules. It turns out that any two neutral molecules attract each other, at least in empty space. And that's something that has really implications in biology and in physical chemistry, organic chemistry, and so forth. So essentially, everything attracts, although of course if the molecules are ionized and they have the same charge, then they repel because the van der Waals attraction is it's a quantum mechanical effect, and so it's proportional to h bar in some way. This equation of van der Waals turned out to be was the first sign that the molecules that chemists were talking about, you know, when you have Na plus Cl is NaCl, that sort of thing. Some physicists who are really enamored of the partial differential equations of Maxwell and those of fluid dynamics and so forth thought that the things that the chemists were doing, which were simply algebraic, in fact they were very simple algebra in very simple forms, they thought that was trivial and didn't really mean anything. And but Einstein in 1905 related something called the viscous friction coefficient and the diffusion constant. Remember, we saw the diffusion constant when we talked about Fick's law back in an earlier chapter. And he related them to the energy, kT, and his equation that he derived was zeta, was the viscous friction coefficient times the diffusion constant is Boltzmann's constant times the temperature. Well, temperature you can obviously measure. The diffusion constant you measure just by watching how fast the molecules, if they're colored or something, diffuse. And in a similar way, one can experimentally measure zeta. That meant that one could calculate Boltzmann's constant, and that was the first time that people were able to calculate Boltzmann's constant. And so once you have Boltzmann constant, you go back to this equation and you have an ideal gas whose pressure and volume and temperature you measure, if you know Boltzmann constant, then you know how many molecules are in your volume of gas. And then you know what the mass of that volume is. You divide by n, and you then have the mass of a single molecule. So all of a sudden the molecules became real, and in particular, they make sense in van der Waals equation. Another separable and separated differential equation is n dot is n squared over b. This corresponds to growth rate of the human population. Turns out that, well, obviously you integrate this by having dn over n squared is dt over b. By the way, when you have such an equation with dn dt, you then basically separate the dn from dt like this, and then you integrate, and so you have a 1 over n, and then t, and you can rewrite that as n is some constant over t minus, big T minus little t. Big T is the time at which the year at which the human population becomes infinite. Presumably Malthus looked at this equation. I think it was Malthus anyway. I don't know what it was. Anyway, and computed 2025 as the time at which the human population will be infinite. In fact, the equation is only good from year 1 to 1970, and it works then if the constant b is 2 times 10 to the 11th years. Then actually this kind of fits the data. So now the meaning of exactness, maybe I should go to the blackboard since this is actual theory as opposed to these blackboards are quite nice. So the meaning of exactness, suppose we have p of xy dx plus q of xy dy equal to 0, and suppose p and q are just general functions. So then what we could do is we could integrate, and we would get phi of xy. We integrate along some contour c, and we start at x0 and y0, then we would have an integral x0, y0, contour c up to xy of p of x prime, y prime, dx prime plus q of x prime, y prime, dy prime. I don't know if you can see the dy prime, but anyway, you can see what. In fact, it's on the screen there. And so you do get a function phi in general, but in general it depends upon the contour. And this is something that you've certainly seen previously when you studied mechanics. If you have a force field whose curl does not vanish, then you can't write the force as the gradient of the potential. But if you have a force field that is curl-free, then you can integrate the force field and get potential. On the other hand, if this thing actually is the differential of some phi, then this is an integral d phi of x prime, y prime along the contour. And then it doesn't matter what the contour is. What you get is phi or phi of phi full anyway, phi of xy minus phi of x0, y0. And that's independent of the contour. And that's, so if the the equation is exact. And once you have that, you then set that equal to a constant b, because the equation, of course, was that d phi is 0. And if d phi is 0, and this term is 0, and then phi of xy is equal to phi of x0, y0 plus some constant b. And then you have an equation for involving x and y and some constants, and you can form, you can find y of x equals whatever. So in this example, I think I'll use the computer for the example. Let's see, I wonder if I can make this. Yes, I can make this. Well, maybe not that much. Okay, so it's a little bit bigger there. So explicit use of exactness and of the criteria of exactness. Here we have P has to be partial phi, partial x. Q has to be partial phi, partial y. We can then integrate the differential equation. And the way we do that is we say that phi is, of course, the x integral of its x derivative, which is right here, p. So it's the integral of p plus some constant that, of course, depends upon y. But we know what p is, so we know what r is. But c of y is an unknown function of y. On the other hand, the second criterion, which is that q is phi sub y, means that q is phi sub y. We have phi equal to this, so that's the y derivative of this structure. And consequently, we can rewrite that as c of y is the integral of q minus r sub y, and we can then imagine doing that integral and adding a constant of integration. And so now we're essentially done. We know that phi is r plus c, which was this equation here, and we then set phi equal to r plus c and set that equal to e. Then r plus c is r, which we computed, and then c is the integral of q minus r sub y. And in fact, now that I see this, I realize that I could have done this integral by hand. Okay. Anyway, an example of exactness is, suppose these two functions are, p is log of y squared plus 1, and q is 2y x minus 1 over y squared plus 1. They're both factorized, so the ODE is separable. It's also exact because the y derivative of p is the x derivative of q. And so then we can do this, do what we just saw in the abstract, namely we integrate p and add an unknown function y. We then get this. Then we take the y derivative of phi and we set that equal to q, and that then has to be the y derivative of this plus the y derivative of c, and combining those two together we get that, and so then letting c equal or phi equal this expression plus c, and knowing what c is now, we get this expression when we set it equal to constant, and then you can eventually unravel it. So that's an example of the use of exactness. Now, sometimes one gets lucky and one can find an integrating factor. And if you can find an integrating factor, then, let's see, maybe that's not so smart because maybe you want that on the board for a moment. So I'm going to go over here and use this board. So what an integrating factor alpha is, you take alpha p dx plus alpha q dy, and so you multiply your differential equation by alpha, and the idea is you pick an alpha that makes the equation exact. And what would that mean? That would mean, of course, that alpha p is equal to the x derivative of something, and alpha q would be the y derivative of the same thing, and then alpha p, the y derivative of alpha p, will have to be the x derivative, which will be phi, the xy derivative of phi, and this then is the x derivative of alpha q. So you need to find an alpha that does this. And if you can find one, bingo, you're done. On the other hand, if you're given an arbitrary differential equation, A, there might not be an integrating factor, or if there is one, you know, how would you find it? An example is, for example, this ODE up here, which is y dx minus x dy. Well, of course, that's a very simple differential equation. P and Q are both factorizable, and in fact, they only consider they're each simple monomials. And on the other hand, it's not exact as it stands, but if you choose alpha to be 1 over x squared, and then multiply both by alpha, you then get this form here, this differential equation. So P is minus y over x squared, Q is 1 over x, and then you find the piece of y is minus 1 over x squared, and Q sub x is also minus 1 over x squared. So you found an integrating factor that makes the equation exact. But another integrating factor is 1 over xy, and that turns it into dx over x is equal to dy over y, which is even simpler, and we just integrate that to log y over y0 equals log x over x0, so x and y are proportional to each other. Homogeneous functions. Now, here things get interesting and have physical implications. So let me just mention what the definition is of homogeneous, and you should think about this definition several times, because when it shows up in a physical problem, you're way ahead of the game because the function is homogeneous. So a function f of x, 1, x2, xn, say, well, I did xk in the example, so let's say xk, of k variables is homogeneous if f of tx1, tx2, txk is equal to t to the n f of x. So I can't write all of those. So this is f of x. So I'm writing x as a vector, x1 through xk. So the idea is if you multiply all the arguments of the function by the same number, t, then that's the same as multiplying the function by t to the n. And so we say it's homogeneous of degree n. And an example is tz squared log, well, I'm sorry, I screwed up, I skipped an equation. Uh-oh. I don't know, that's lost forever. It's a nice eraser. So the equation, the function that's homogeneous of degree 2 is z squared log of x over y. So you multiply x, y, z by t, and what you get is tz squared log of tx over ty. Well, this is t squared z squared log of x over y. So this is homogeneous of degree 2. Now, Euler realized that functions that are homogeneous of degree n have really interesting properties, and what he did was he differentiated this expression with respect to t. So we have ddt of f of tx, and that would be a sum. Remember, f of tx is the, it would be partial of f of tx with respect to txi times the partial of txi with respect to t, and it would be summed I equals 1 to however many, well, k variables there are. So this is one way of writing the t derivative of f. And this thing here is just a sum I equals 1 to k. This is xi. And this, if we evaluate this at, well, it's partial f of t x with respect to t xi. Now if we set t equal to 1, what we get is that the sum here of xi, I equals 1 to k, xi times the partial of f of x with respect to xi is equal to well, it's equal to the time derivative of f of tn. That is to say, if this is homogeneous, in other words, if this is homogeneous, then this is d by dt of f of tx. But if it's homogeneous, then that's d by dt of t to the n f of x. And so that is n t to the n minus 1 f of x, set t equal to 1, and we have n f of x. So the result, which is one of Euler's many theorems, is this expression. And let me put it on the board here on the screen. It's this expression, 7.109. xi times the partial of f with respect to xi is n f of x. That's if f is homogeneous of degree n. And if it is, and there are many physical applications of this, and so it's important to become familiar with this. There are examples in thermodynamics, the internal energy. evidently is a first-degree homogeneous function of things like entropy, volume, number of molecules of kind J, and the reason is that if you increase the number of molecules, the volume, and the entropy, well, that's sort of like doubling or tripling the system, and consequently the internal energy will be doubled or tripled. And so what you say is that U of Ts, Tv, Tn is T times U of SVN. And those partial derivatives, and of course these partial derivatives were taken, well, they're normal partial derivatives, so they're partial derivatives, the idea is they're derivatives where all the other variables except the ith one are held constant. And so for some reason in thermo class one makes that very explicit. Alright, the temperature turns out to be defined as the partial derivative of the internal energy with respect. This is certainly a robocall. The temperature is the partial derivative of the internal energy with respect to the entropy. The pressure is minus the partial derivative of the internal energy with respect to the volume. And the chemical potential is the partial of the internal energy with respect to the number of particles of type J. That's the Jth chemical potential. So the change in the internal energy, well, it's going to be partial of U partial S ds and so forth, so that's TdS minus PdV plus this sign. This minus sign is because of this minus sign which was put in there. Then Euler's formula tells us that that the internal energy then can be expressed as, in other words, 1 times f of x is the variable, the independent variables times the partial with respect to them. And so the internal energy is the derivative times s minus p times v, minus p being the v derivative of u, and then all these derivatives of uj and j. So this formula for the internal energy is actually an example of Euler's theorem for n equals 1. I can't help but remark here that if the energy density of empty space is positive, and as far as we know it is slightly positive, then the internal energy rises as it expands. And so, in other words, if the universe doubles in size, well, there's twice as much volume, so the energy, the internal energy at least, doubles. And the definition of pressure then implies that the pressure on the universe is negative. And so the point is, if the density of empty space is slightly positive, then the universe will naturally accelerate. Quite apart from general relativity, one would just say that thermodynamics would require it to expand because the pressure would be negative. And that's what has been observed since just before the turn of the century, this century. And we call this energy, dark energy. Turner at University of Chicago coined the term. He, by the way, is a very clever lecturer, very amusing lecturer. And so anytime you can listen to a Turner lecture lecture. It's worth doing just as entertainment, let alone physics that you learn. Let's see, I was going to say something else about this, but I've now forgotten what it was. Does anybody have a question about dark energy? By the way, the actual situation is that roughly 70% of the energy of the universe is dark energy. Around 30% then is the energy of matter. And on the other hand, the energy of normal matter is only about 5% of the energy of the universe. So most of the matter is what's called dark matter. So getting back to the thermodynamics here, this formula here allows us to express ds in this form, and that then leads us to these various relations, partial s partial u is 1 over t, and so forth. Partial s partial v is p over t, partial s partial nj, with a minus sign is the jth chemical potential over t. And the entropy, on the other hand, is not a homogeneous function of u, v, and n. The formula, approximate formula for the entropy of an ideal gas is this expression here. And so if you multiply u, v, and n by the same number, then you'll get a t out here from n, and in here you're going to get a t to the 3/2, and then you have to take the log of that, so it doesn't turn out to be homogeneous. The Virial Theorem. This is an application of Euler's formula, and it works if the potential is a homogeneous function. So let me go through that. In fact, maybe I'll do this maybe I'll do this on this board, or is the board too far away? You're going to need opera glasses or telescopes in this classroom. So, right. So this Virial theorem, first of all, I'm working here in the context of Newtonian non-relativistic mechanics. Presumably, one could consider quantum mechanics or relativistic mechanics. Anyway, let's define the virial for n particles with 3 capital N coordinates, xi and momenta pi. So this is called the virial. Why it's called virial, I don't know. If one of you wants to Google that and let us all know, that'd be nice. Anyway, in terms, the momenta, of course, are the partial derivatives of, or rather the time derivatives of the momenta are, of course, the forces, and the kinetic energy can be written as V1, P1 plus V2, P2 plus VK, PK, all of this divided by 2. So why did I write that big equation? Let's just write it this way. So if we, in terms of P dot and F and T, we can write the time derivative of the virial. It would then be a sum where you take the time derivative here, you get VI, PI, and do the time derivative there, and this is XI, FI. And so this sum here is twice the kinetic energy, and what's left then is some Xi, Fi, I equals 1 to 3n. And so what we can do now is take the time average of this equation, averaged over a long time, a time long compared to the characteristic times of the problem. And the characteristic times for hydrogen atoms might be the time that an electron takes to go around the proton. Or if you're talking about the solar system, it'd be the time that maybe Jupiter takes to go around the sun, or something like that. If you're talking about galaxies or clusters of galaxies, then you are talking probably billions of years. In any event, what you expect is that this would be G of big T minus G of 0 divided by big T. And what would this be? Well, this would be twice the time average of the kinetic energy plus the time average of the sum, I equals 1 to 3n of Xi, Fi. And for most systems, this thing is 0 in the infinite T limit, at least if the system is somehow bounded. Let me put, oh, this part is on the screen, okay. So what we can say then is that this is equal to 0. And now if we say that Fi is minus the partial derivative of B with respect to Xi, we then have that 2, the time average of the kinetic energy minus the sum of Xi partial B partial Xi minus the time average of this is equal to 0. On the other hand, if V is homogeneous of degree n, then this is equal to NV. And so what we get then is the time average of the kinetic energy is n over 2, that's the 2, times the time average of the potential energy. And so this is called the Virial Theorem. And so what you need is that this is homogeneous. The potential V of x1 xk is homogeneous of degree n. If that's the case, then the Virial Theorem is that the time average, or to put it differently in more colloquial terms, that on average the kinetic energy is n over 2 times the potential energy. So there are all sorts of examples of this. As I said, this is really important in physics, and you can see that it all follows from Euler's theorem and then the definition of homogeneity. So Coulomb forces Gravity goes as 1 over the distance. Potential goes as 1 over the distance. Electrostatic potentials also go as 1 over the distance. And so they're homogeneous of degree -1. And consequently then the time average of the kinetic energy is -1/2. That is to say, n being -1 divided by 2, so -1/2 times the time energy of the potential energy. Now, as I said, it's one can avoid. Oh, I forgot to pay the videographer candy. Is anybody starving and need a candy?
I'll take one.
Good catch. So it's one can save a lot of trouble and avoid a lot of typos and mistakes by using natural units. In other words, setting h bar and c equal to 1. There are other things you can also set equal to 1, but you have to be careful not to set too many things equal to 1. You don't want to set h and h bar both equal to 1, otherwise you have too high. So in natural units, the energy of an electron circling about a proton of mass, an electron of mass m, moving with momentum p, circling about an around a proton, a distance r from the proton. And here, not only am I in natural units, but I'm afraid I've also set the electric constant equal to 1. So I'm in a particular set of, I'm in convenient electrical units, not MKS. Or equivalently, we use the charge of the electron in those units. The uncertainty principle then says essentially that RP is greater than 1 because h bar is 1. This is very qualitative. And so what we're going to do is we're going to set RP equal to 1 to estimate the energy of the ground state of hydrogen. So if we set RP equal to 1, 1 over R is P, and then E is P squared over 2M minus E squared P. To get the minimum, we differentiate, we minimize the energy by setting its P derivative equal to 0, and we get this. And so now we know what P is. On average, it is ME squared. And so substituting in, we get that T is ME squared squared over 2M, which is ME to the 4th over 2. The potential energy is minus E squared P, or minus ME squared. And these satisfy the Virial Theorem because T is then minus V over 2. So take this, divide by 2, multiply by minus 1, you get T, which is what you expect because the Coulomb force, the Coulomb potential is homogeneous with degree -1. If you then go back to real units, what you find is one way of doing that is to multiply by c squared and divide by h bar c squared. And we know mc squared has to be the mass energy of the electron, and that's 511 kilovolts, or half an MeV. It turns out that E squared over h bar c, in the units I'm using here conveniently, is 1 over 137. This is the fine structure constant in these electrical units, and you multiply that out, you get 13.6 eV. It's remarkable that one gets exactly that number. I think I took this from
this example is originally, I think, due to Victor Viscous, who used to be a professor at MIT. But he may have gotten it from Heisenberg, so where it came. It was very cute. Dark matter. Well, in 1933, Zwicky applied the gravitational version of the Virial Theorem. Again, V is minus a half, T is minus a half V on average. And he was looking at galaxies in the Coma cluster, which is a supercluster of galaxies. And what he found was that the galaxies were moving too fast for the number of stars that he computed were in the Coma cluster. And so he found that it was inconsistent with the Virial Theorem. And not wanting to give up the Virial Theorem, he said that there was some matter there that he called dunkel, which is German for dark. Anyway, it became called, other people call it dark matter. Another person, I forget, some woman, somebody remember her name? She was working in the United States, and she also did observations. I think she was looking at stars moving around galaxies, whereas Zwicky was looking at galaxies moving around in a cluster of galaxies. And she also said that there was some matter that we could not see. The right name for this matter is transparent matter or invisible matter, but unfortunately Zwicky's term dark matter has caught on, and so we're sort of stuck to it. But I encourage you to violate that silly convention, because it leads people to think that if you looked out into space, the dark matter would make it impossible to see stars behind. In other words, if you had some cluster of galaxies here, and then there was some other bright objects behind the cluster of galaxies, the dark matter would make it impossible to see them. But that's not true. The dark matter has no effect on the light coming through, except gravitationally to bend it, and perhaps to lens it. But so the correct term is transparent or invisible matter. In fact, I think invisible is the most amusing term. Harmonic forces are homogeneous of degree 2, and so there this equation takes, the Virial Theorem takes a simpler form, namely that on average the kinetic and potential energies are equal. And that's then true of things bound in harmonic potentials. Okay. So now the next topic is the Legendre Transform. And I think I'll go to the blackboard at least for the beginning of this before we start doing examples. Let me see what the time is actually. 6:34. All right, so we're nearly out of time. So let me move the screen, the stuff on the screen, so that you can't read. Oh, it is correct on the screen. So Legendre's transform, or the Legendre transform, is to illustrate that. Let's imagine we have a function a of x and y, two independent variables x and y, and so we would say dA is the x derivative of a times dx plus the y derivative of a times dy. Now, what you can do, suppose you decided to define v as the y derivative of A. And that we define a new function b equal to A minus V1. So what is dB? Well, dB is going to be AX dx plus AY dy, because that's dA. And then we have minus dVy minus V dy. But V is AY, so this is minus AY dy. And you see this has been cleverly arranged so that this term is canceled by this term. And so what we have is that dB is simply AX dx minus Y dV. So this suggests that B is a function of X and V. And we can actually make it a function explicitly of X and V if we solve this equation. Namely, we can write we have to solve for y to get rid of y, and so b is equal to a of x and y minus v y. We can solve this for y. Well, what we have is that vy is equal to a minus b. So y is equal to a minus b over v. But you see, a is a function of x and y, and I think we can leave b the way it is. But this means that y occurs in two places, and so this can be, it can be non-trivial to, in fact, it is in general humanly impossible to solve for y as a function of x and b. But if you can, then what you have is that you have b of x and b is equal to a of x, and then y of x and v minus v y of x and v. So you can solve this equation for y as a function of x and v, then you can actually make b the function of x and v in this way. And it turns out that in physics, the theories that we normally consider are ones where you can do this Legendre transformation. And it could be that, well, what's actually been going on is that any theory that for which the Legendre transformation didn't work, well, that physicists basically skipped that theory. And so there are various areas of physics that just haven't been explored because they don't allow you to do this sort of thing. So going back to a of x and y, we could also define a new variable as u, the x derivative of a, and a new function c, which would be a of x and y minus ux. And in this place, we would have dc is equal to a sub x dx plus a sub y dy minus dux minus u dx, and u, of course, is a sub x, and so this, I can replace u by a sub x. Now we see that we managed to cancel two terms, and so dc is a sub y dy minus du times x, and so this suggests that c is that c equal to a of xy minus u x is actually a function of y and u. But to do that, what we have to be able to do is we have to be able to write c of u and y as a of x of u and y minus u times x of u and y. And so we have to solve this equation here in such a way that we solve for x, and we can then know what x is as a function of u and y. And then we can make c explicitly such a function. And one could also do two transformations. One can say u equal to a sub x and v equal to a sub y, and d equal to a minus ux minus vy, and in that case we get that the differential of v is, and I'll just skip the intermediate steps, minus x du minus y dv, and so we can write d of u and v as a of x of u and v, y of u and v, minus u x of u and v minus vy of u and v. So one can rewrite the thing as rewrite this as a function of, this is u, not y. And this is another robopole. So let's go to an example here, and examples are very important because they're the examples of not only of mechanics but electrodynamics, of classical field theory, of general relativity, of quantum field theory, and so forth. So this sort of stuff is used throughout physics, and so it's important to be comfortable with it. So in particular, let's start with a Lagrangian that is equivalently an action density that is, or time derivative of an action, that is itself time independent. So we want a Lagrangian that's time independent. Then dl is partial L partial Q, dq plus partial L partial Q dot dq dot. L, of course, being a function of generalized variables Q1 through Qk, say, and time derivatives of Q1 through Qk, but we say it's independent of time explicitly. There's no time explicitly, otherwise we'd have partial L partial T dt. We can then define the new variable P as partial L partial Q dot, and the Hamiltonian as PQ dot minus L of Q and Q dot. So then dH is PQ dot plus Q dot dP minus dL, and dL is this, that. Now what we see is that this term cancels that term, and so dH is Q dot dP minus partial L partial Q dQ. And So that suggests that the Hamiltonian then is so defined as a function of position and momentum. But to really make it so, we have to properly solve for q dot in terms of q and p. Now, what you may notice is that all the theories you've been taught in school are ones where the Lagrangian is quadratic in q dot, and the Hamiltonian is quadratic in p. And so, if that's the case, for example, the Lagrangian being mq dot squared over 2 minus m omega squared q squared over 2. The fact that this is simple isn't critical. It's that L is quadratic in the time derivative of q. In that case, P is partial L partial q dot, and that's just mq dot. So you can immediately solve for m in terms of P, namely it's P over m. When L is not quadratic in q dot, you then have a problem. And a graduate student named David Amdahl and I have looked at this, and in particular, we've developed ways to approximate the integrals of such theories. And it's just amazing how, when you depart slightly from the quadratic case, L is quadratic in q dot, you depart from that just slightly, things just go haywire. But we are out of time, so let's just quit. Why don't you, is there a question? All right, there should be more questions. Anyway, as I said,